7:30 class, huh? You know, by 9 o'clock you're done, so it's great. We usually tend to let go from home. First year? Well, first year student. Okay. Second year? Alright. ESMS? Alright. So where are you from?
I'm from Sept30.
Wow.
I'm also from
San Diego?
Yes,
San Diego? Oh, but originally, not from San Diego,
Oh,
right?
from China.
From China. Anybody local? Alright. From the Far East? China, and so let me hand out the first handout, and then we'll talk about the way the structure of the class is. Okay. So this is 251c on Philippine equivalent. So I have office hours. Office hours on the 6/4, and office hour is on Monday from noon to 1:30. And by appointment, if you cannot make that time, just email me anytime. I'm normally in my office, so I can meet with you anytime you like. We have no TA for the course. I could not find anybody who took the course before and available for TA. So I'll do all the, TA question answering, and so on and so forth. We'll set up the piazza later on, so that way you can actually, who have used piazza before? Great. So you can ask questions there. It's very useful because, I normally wait about a few hours for your friend to help you, and if nobody can help you, then I'll jump in and help, right? So the class is structured in a way that, it is a grad level course, so the homework I hand out, the homework, it will be a book. I'll talk about more about it later on. But the handout, the homework will not be graded. I'll hand out the homework, you do the homework, I give you the solution, right? So basically, it's not graded, it's on your own. Any question regarding the homework, just talk to me, or, make friends and talk to your friends. There'll be midterms on the November 6th, and midterms in class, course book, course note, in the sense of you are allowed to bring, one regular sheet of notes. You can write, both sides your own notes, and that way it's more useful for you to prepare your own notes because, you know what you know, you know what you don't know, right? It's 30%, and then the project is 50%. This is the final project. And the way we work on the project is that you will form a partner, look around. At the end of the day, you should find a partner, right? So today, normally I lecture for about half an hour or 35 minutes, 5-minute break. For you to use, because I think an hour and 20 minutes is too long for lectures. And, by the time you get to 30 minutes, you'll be sleeping anyway. So it's a good break between, in an hour 20 minutes, a break, about 40 minutes. So today, during the break, form a partner for the final project, right? So the final project will be, there's a handout back there somewhere. Okay? So the project will be 2 persons, and then you would form your project and then propose it. So on the November 25th and 27th, I would imagine that we have about 10 to 15 projects in the class, depends on how many students remain. Then we'll break up into 7 and 7, right? So you have 10 minutes per project to present what your project is all about. We have feedback and so on and so forth. So the first day on the 25th, the first 7 group will present the project, and then the next day, the next group of 10 project will present. Right? There's a handout, so pick up the handout. Those who come in late. And then there's a final project presentation, 25%. That's the final day, the final exam. Final exam, you have 3 hours, so we spend all 3 hours for you to present your final project. And then about 5 days after that, you have final report. So you have 5 days to work on the report, and that counts 25%. Is that clear? Okay? So basically, it's heavily weighted toward the project. And the reason being is that, grad level courses, it's kind of hard for me to ask final exam, right? Because either I ask very difficult questions or else. So it's hard. Right? And it's better for you to learn the materials by doing projects. So if you, for example, if you work on machine learning or any other project, you can figure out how to apply wavelet or filter bank, right, in your applications, in your research, in your interest, and so on. I can guide you, right? And you can find out more about filter bank and wavelet and why it's useful. Who have heard of FFT, DFT? You hear about it, right? So you can think of filter bank as a generalized version of FFT, right? It's a front end process where you take a signal and divide it into different bands of frequency, and so on. And the way that we design the filters, the way we structure out the whole structure is different, right, than FFT. If you think about it, think of it as just an FFT, right? And we use FFT in many things, right? From analysis of speech to estimation of parameters and so on and so forth. So it's really a very general way of thinking of filter bank. And that's why you can plug and play, right, filter bank into all applications very easily. Okay? Any questions on how the course is structured and graded? It's clear? Okay. So, this is more details on the project and the textbook. So I did not order a textbook because what happened is that I wrote a textbook with one of my colleagues at MIT, and he retired, so he had about 20 copies. He said, you can have it. Okay, great, send it to me. So I have 20 copies, we have 40 students. So that's why you need to form a partner today. And the way it works is that your partner and yourself will get a free book from me. Okay? Right? Is it on?
Yes.
You got a free book, and then we have also a fund that we set up for student outreach. So if you want to donate to that fund, that's fine, but it's not required. But the book come for free from me, right? So today, during the break, talk to your friends, form a partner, and then on Thursday I bring 20 books in. I give each team a book. All right? So you're the only class that have free books. And so Mona just came in, and so we have a system in the back. So that camera system right there is called EVT. What's the website, Mona? EVT?
Yeah, it's learn.evt.ai.
What?
So it's evt.ai.
EVT.ai.
Yep.
We will send information on how to access the lecture. So it's pretty cool. So he will videotape my lecture, and then you can actually search based on the speech. So normally in a lecture, you have to watch. You could not figure out when do I mention wavelet in my lecture. So it's hard to actually go and step through the lecture and find out where do I mention wavelet. For this system, it will actually mark. You can search on wavelet. It will mark where do I mention the word wavelet. Right? So that way you can actually step through and understand. You can be able to. You don't want to see me. You can extract me out. So we just a whiteboard, right? And so it's a pretty cool system. All right. Okay. First one will be handed out on Thursday with the book, and the idea. So the prerequisite, right, for this class is DSP. Okay, and the class. Okay. So what should I review? Okay. Who took my class? Or who took 161A? All right. So we should help the others on what we should review. None? Effective. Okay. let's go slowly, right? Let's start, to talk about signal processing, digital signal processing, talk about Fourier transform, and look at the way we're doing convolutions, look at sampling, and then go to different kind of filter that's useful, especially for image processing. Interface is important. Looking at different ways to design filters, and the fast way of implementing EFT. A day and a half. Okay, good. Let's see how it goes, right? So most of this class, at the end we will talk about continuous time, but most of the time in this class, we'll talk about discrete signal, right? Okay? And the way that we're representing discrete is by sampling point. Okay? So we said x of n, like that, and here, taking on integer value 0, 1, 2, 3, and so on and so forth. And then we representing a system, right? As a black box. And then do something to the signal, and the output is y of n. Right? That's typically very broadly speaking, how we representing discrete time system and signals. Okay? Now, of course, we can describe y of n in any function of x of n. Right? But there's a special class of systems that make it easier to analyze. Right? So what kind of system do we normally talk about? Or do we normally constrain our discussions so that you can do some analysis? Linear time analysis. So if it is linear, this will work. I bought this one 2 years ago and didn't use it. So try it. Okay, so typically we constrain the system to be linear and time invariant, right? To make it easier to analyze. So why is it linear is easy to analyze? Why is it linear? Make it easier to rewrite equations and so on and so forth. What does linear means? How do I know? How do I test whether the system is linear? There's a handout in the back, okay? So for those who come in late, give a handout.
When you put a signal into the system, and if you sum, pretty much if you sum two inputs, put them in the system, that's the same as putting each in the system individually and summing the output. Pretty much that you can recover.
Okay. So linear make it easier to break up the input into components. As long as you know how this component, right, the system work on the component. You add them together, this side we add, right? Make it easier because typically signal x of n can be decomposed into impulses or and so on and so forth, right? So linear make it easier to analyze that way. How about time invariant? How do I test whether something is time invariant?
Is there, when there is a time shift of your input signal, your output signal should also represent, also show a time shift?
So it doesn't matter when you turn on the system, right? Okay, that means time invariant. Turn on that. Yesterday it should react exactly the same as today and so on and so forth. Today we did yesterday shift, that time shift, right? And if that's the case, then the system we put here x of n, this is called impulse invariance, right? Impulse response. All you have to do is knowing how the system react to an input, then you know how the output is going to be reacted, right? For LTI systems, the output could be a summation of the input response and the shift of x, right, in k. Okay? And this is convolution. Okay, this is the definition for convolution. Linear convolution. Right? So now make it easier now for you to analyze any output, because the output only depends on the impulse response and the input, right? So once you measure the impulse response, and how do I measure the impulse response? I just put delta n into here. The output will be x of n, right? That's the definition. Okay? So that's all I have to do, okay? For LTI systems, I first find out what the impulse response is, and then I can know how to find the output for any given input, right? Make it easier to analyze. Okay? So now if I know convolutions, what else can I talk about? So now this is time domain analysis, right? Here we have time versus frequency. How do I introduce frequency into the system?
Yeah, you can, if you convolve, or actually, yeah, you end up convolving, I think if it's technically convolving or just multiplying, which is a convolution, with a phase, like an e to the,
Exponential.
yeah.
Okay, what he's saying here is that this equation describes how the input and output are related, right? For any input, what if I put in a phasor, right? E to the j omega naught n as an input, right? And omega naught take any frequency, right? Then what's the output? You can plug this into here, okay? And then after about 2 lines, you get the result as saying the output will be e to the j omega naught n, same as input, scaled by these terms. And how do I see this? Plug in e to the j omega naught n to here. You have e to the j omega naught quantity n minus k, right? And that breaks up into 2 different exponent terms. The first term is e to the j omega naught n, it's right here. And the second term is e to the minus j omega naught k, second terms. That's it, that's all I'm doing. Right? And this is beautiful in the sense of, wow, for an exponential input, the output is exactly the same as the input, scaled by a quantity that only depends on the impulse response. And that is why we define this as the discrete time Fourier transform. Right? And these definitions, you know, you can define this for x of n, x of n, y of n, anything. Right? And the range of omega naught is periodic. Why is it periodic? Because e to the j omega naught plus 2 pi n is the same as e to the j omega naught n, right? But e to the j 2 pi is 1. So we know that the range, right, for the discrete time Fourier transform, this is discrete time Fourier transform, right, is periodic. of 0 to 2 pi. That's why in the discrete time Fourier transform, we only plot in the range of 2 pi. Either minus pi to pi, 0 to 2 pi, whatever it is, it's periodic. If it's not periodic, you have a problem. Yes? Here? Here? Why? One more time? Why you this is multiply? So why this is the case? Right? So this one here come from, so if this is the case, right? So you have, okay, let me plug it to here, okay? Summation in k, x of k, e to the j omega naught, and minus k. And this is summation in k, so this one can be pulled out. And what's left is this guy. Oh, well, it's a dummy variable. You can put n into here, doesn't matter, right? It's just a dummy variable. Okay? So is that clear? How frequency get introduced into LTI systems, right? And from here, it turns out that if you take the Fourier transform of y and x, then y e to the j omega is a product. Okay? That's why convolution in the time domain become multiplication in frequency domain. And that gives you the idea of filtering. Okay? Right? This one here is saying that. So now, right, you can talk about, you have an input spectrum X, right? And the system response H. Then the output Y is a product. Okay? For example, let's say x e to the j omega. Right, so now I'm going from minus pi to pi. Let's say this is mostly a low pass signal, right? Speech. Our speech is low pass, right? We cannot really talk very loud, very high. Then you have a higher frequency, right? So most of the time it's low frequency. So it's about, well, right here, something like this, right? And very low out here. And of course, it's real time, so something like this. Okay? So then, if it's a filter, it's a low pass filter, let's say minus pi over 2 to pi over 2. And let's say, you hear the noise in here, right? So I have my speech with some noise. Let's say the noise, it's not really high frequency, but let's assume it's over here, some noise, right? Then the idea of filtering here is that the output, right, is just a product. So it's very easy to visualize in frequency. Much harder to visualize in the time domain, right? So the output will be basically, the low frequency, right? Okay, here's X, here's H, that's Y. Okay, and that gives us the notions of filterings. Okay. And all kinds of filters, right? Because now you see that depends on how you choose the filters. Right? Take a look at this. The filter here can change the phase of the signal, right? Because X is a complex quantity, Right? Look, anything Fourier transform is complex. Right? So in general, right? This is complex, that's complex. So you have a phase and magnitude. Real part, imaginary part, and so on. Right? So if I don't want to change the phase response of my signal, then this H here should have a spectralized phase. It's either linear phase or zero phase. Right? I only want to change, what I'm plotting here is a magnitude, actually. Right? A magnitude. Okay? Because the phase response, I cannot really plot, right? So it depends on how I choose my filters. If my filter has linear phase, right? Then linear phase filters, right, does not change phase of X. I only change when I change the magnitude. Okay? And that's why linear phase filter is normally used in practice. Anytime that your boss tells you to design filters, you should use linear phase, right? Because really, you don't want to change the phase response of your input signal. You only want to change the magnitude response, but not the phase response. Is that clear? Right? And this periodicity is only come from sampling as well. Who remember why it is periodic after you sample? So let's talk about sampling. And periodicity. We know that by definition, the way we reconstruct the discrete time Fourier transform, it is periodic. Right? How do I observe the same observations through sampling? Because sampling also gives me a discrete time signal. Right? So who remembers sampling? Going from t, right? X of t. Let's assume there's a signal, X of t, like this. And what do you do when you sample? You multiply with sampling, right? S of t, sampling poles. Sampling poles are basically equal space, period t, and so on. Right? And after you do that, what do you get? You get exactly the signal right here, but you have sample at those points as t, 2t, and so on and so forth, right? So now you have the signal that is there, and so on. Those kind of signal, right? X of m. Okay? So in frequency, now this is continuous time frequency, the big omega. Can you guys see down here? Maybe? No? Okay. All right. So let me bring it here, okay? Yihan, can you remind me when I should take a break? Thank you. That clock is wrong, so. Okay, sampling. Should be about 810-ish. Okay. So t, x of t, right, multiplied by the sampling pulse S of t, okay? To get and so on, right? Okay? So let's talk about the Fourier transform. Is this a low pass or high pass signal? It's slowly varying, so probably like something like this, right? Okay? How about the spectrum for these impulses? Who remember the Fourier transform for a train-up impulse? 2 pi over t, very good. Okay. Excellent. So what did we get? Multiplication in times equal to what in frequency? Convolution. Right? So now we take the original spectrum, convert with the impulse. What do we get? We get this, repeat it, right? So the way I'm plotting right now is that overlap. So it be like this, right? With some overlap. And that overlap here is aliasing, right? That guy right here. When you have aliasing, what do? Why do you have aliasing? Sampling rate is too slow, right? To reduce aliasing, what do? Faster, sample faster. You have to decrease t. Sampling faster, meaning more sample, right? T has to be smaller. When t is smaller, what happened to 2 pi over t? Well, sorry, t is smaller. What happened to 2 pi over t? Larger. That's why you have separation. Right? So this here is small t, right? And let's make it t prime, okay? T prime is larger. So now t prime is smaller than t. Okay? So if this is the case, then you have a same spectrum, but now it's separate, right? So you have this guy here and so on. T prime. Is that clear? And the mapping from j omega to the omega that we have here is just pi over t, right? So that's why this is 2 pi 4 pi, and that's why it's periodic. Okay? It's periodic because of the sampler. So if you have any spectrum, discrete time spectrum, that's not periodic, it's wrong. If you give me any plot in the, that's not periodic, then it's wrong, right? As long as the signal is discrete time, the Fourier transform is periodic. Good time? Okay. So Yihan tell me it's a good time for a break. When we come back, right, we'll go to looking at filtering. Okay? We'll talk about different kinds of filters and so on. So during a break, so for those who are coming late, you need to form partner, 2 per teams, for your final proposal. And the way it works is that I will give out a free book per teams. This is the only time it's going to happen, right? I got free book for my co-author. I'll give to you, right? So each team have a free book of 2 students. All right? So decide right now, and then, one second. And then on Thursday, I will give out each team a free book. Yes?
So the team would be graded the same way, right?
One more time?
The team is going to be graded the same.
Yeah, the team will be, so you will have 1 common grade per team for the final project. Okay? 5-minute break. And Yihan will tell me when to get started again. Yihan? Yes. Tell me when to get started again. So talk to your partner, friends around you, teams.
Registering the class and just auditing it.
Auditing.
Yeah, is this okay for you?
Auditing is fine.
Okay.
Yeah, but you don't have to form a team.
Yeah, for sure.
Okay,
I'm
good.
just taking your permission.
That's fine.
to audit.
Yeah, that's fine. Mhm.
Do you mind I can audit this class?
Audit is fine.
Yeah, thank you, because I was working at Qualcomm and I'm working on 5G products.
That's fine.
Yeah, so I want to learn this kind of stuff.
Sure, yeah,
Thank you.
sure. Hi. How you doing?
Also, are you having office hours today?
Today
1 to 1:30.
1 to 1:30?
Yeah.
Okay. I don't have any questions about the class, but I have some kind of master's class.
Sure.
questions.
Yeah, definitely.
Thank you.
Yeah, stop by. Very good. One 1:30 to 2. Yeah. Okay. Okay. Let's take 1 more minute to wrap up, and then we get started again. And remind me at 8:45. Okay? So as I said before, I hope that you found your partner. It's great that to see everybody talking to each other. It's great. And again, I will hand out a textbook, one per team on Thursday. And there's no requirement if you want to donate to the core fund. We set up the core fund for education and outreach purpose for our department. Okay? All right, so I forgot to mention that to do any of this stuff, I need to talk about Z transform, proper functions, and then pole and zeros. That makes it much easier when we describe system and so on. So let's quickly review Z transform. Okay. All right. So we said before that the Fourier transform, right? The Fourier transform, discrete time Fourier transform, x of e to the j omega, summation in k, x of k, e to the minus j omega k. Okay, that's the definition. What could be a definition for the Z transform? I can put n now, right? N, okay, doesn't matter. Just a dummy variable. What could be the corresponding definition for Z transform and why? X of n Z to the minus n, okay? So the Z transform and Fourier transform are related, right? If we plug in Z equal to e to the j omega, then I get the Fourier transform. So what happened here is that if I look at the Z plane, unit circle is one Z plane, right? And the Z plane basically describe a general complex variable, right? If you pick at any point here, there's an angle omega. The radius is r, e to the j omega, right? So the Z plane is basically a plane to describe complex numbers. Yes? You can describe it in terms of real or imaginary axis, or radius and angles, right? And this is useful in a sense. Why is it angles useful here? Because you can see here is that omega, we know that it's periodic. And this is periodic. This is zero angle, right? And so on. 0, pi over 2, pi, 3 pi over 2, 2 pi back to 0 again, right? So now this is very easy to see and remember, right? Omega, right in this form here is periodic, okay? So the Z transform is just the value of your systems in the general Z plane, right? Where Fourier transform is only on this unit circle, right? So this is when Z equals e to the j omega, I equal to 1. So basically, I equal to 1, right? That's the unit circle. Okay? So that gives us a bit more general way to describe systems, right? And you can remember before that, a bounded input, bounded output, stable system, right? Will include the unit circle. And when Z is converging to omega, right? Okay? So the Z transform, because this is now in general, I can describe a system now in terms of the pole zero plot, right? Pole zero, or in a Z plane. Okay? I can say, there are many ways to do this, right? One way is to say y of n is, let's take an example, 1/2 x of n plus 1/2 xn minus 1. That's how I can describe a system by taking the input and do something with it. That's one way. Yes? Can you describe for me what this system is? What is it doing? It's taking the current sample, it added with the previous sample and take average. That just smooth out the signal. That's just averaging, right? This one averaging. Taking average. You have a lot of varying signal. You take average. What happened to your signal? You smooth it out, right? What is smoothing out means in frequency? What could be the corresponding way to write a system in frequency? I'm now just showing you a different way of describing the same systems. And I'm going to make the transition over to Z transform, right? Pole zero plot and so on. Like a low pass filters. Okay, that's right, because I'm smoothing out the signal. But how do I know exactly the value for H? I can take the impulse response. What is X of n? Assuming that at rest, how do I find X of n? X of n is the output when the input is delta n. Assuming at rest, okay? And what is the Fourier transform for that system? What is the Fourier transform for delta n? It's 1. It's 1/2 plus 1/2 e to the minus j omega. Right? And that's it, basically 1/2, 1. I'm going to pull out half the phase. And I will get 1/2 okay. Here you have n, x of n, you have 1/2 at 0, 1/2 at 1. Right? So there are many ways to describe a system, right? One way is by input and output relations. One way is by plotting out the impulse response, or describing it in terms of phase and response, right? And the reason why you can do this is because the signal itself or the system itself is symmetric. There's a center of symmetry right here at time 1/2. You can show later on that system that is linear phase, right? Linear phase system here is the impulse response is either symmetric or anti-symmetric. So if we notice that the impulse response is symmetric, how do I know it's symmetric? Because the center of symmetry in the middle, where everything is reflected, right? That's symmetric. Okay? If you have such a signal, then the Fourier transform is basically can be written in terms of the phase response times a real value signal. Pull out this phase here, basically shifting this one around 0. Right? So that's 1/2 there. That's 1/2 right there. That's your phase response. And then what's left is 1/2 e. It's just a cosine term, right? This is a pair of exponential. This is just, this distance here is omega over 2. That's omega over 2. That gives you 2 cosine of right there. Okay? So we'll have more example later on to taking any symmetric impulse response and quickly write out the discrete time Fourier transform by looking at the symmetry. Okay? So again, that three way now, right? One way is there's a time relationship, impulse response, and then frequency response. Any of these are equivalent, right? Take it one step further now, right? I can do exactly the same thing now for Z transform. So x of Z will be 1/2 1 plus Z inverse. Can you guys see blue down there? Yes? Okay. Right? That's just basically it's 1/2 plus 1/2 Z inverse. Pull out 1/2. Okay? So how do I describe this system in pole zero plot? Where are the zeros? At what value of Z this becomes 0? -1. Right? The same system now can be drawn in pole zero plot. -1. And if I give you this system right here and ask you to plot the frequency response, magnitude, right? Can you quickly just ballparkly plot them? How do I plot the frequency response based on pole Z-plane, pole zero plot? This right here is where? Here. Unit circle. Right? Where is this point? It's right here. See that? That's 0 omega equal to 0. That's pi over 2, pi, 3 pi over 2, 2 pi. As I'm going from here to there, okay, let's say 0 to pi, and go the other way to minus pi. I'm going from here to there, here to there, and measure the system response. Okay? What happened when I'm exactly at pi, on the 0? What's my value? What's the definition for zeros? The system will be at equal to 0, right? So I know that there'll be a 0 here, 0 there. Whatever happened there, got to go to zeros, right? As I walk away from the 0, what happened to my response? I feel stronger, right? 0 will get all my energy. I'm like that, right? Black hole. Done. Okay? And when I get out of the 0, what happened to my response? Stronger and stronger. So I expect it to be increasing. Right? At what frequency here, I'm strongest? Farthest away from the zeros. On the unit circle, at what frequency, where am I? On the unit circle, farthest away from the 0. Right here. That's the strongest point. Right? So I expect it to be like this. I want to be symmetric, so. I'm not find out exact the value, but roughly speaking, that's what the shape's going to be. They are symmetric. Why they are symmetric? Because it doesn't matter where you're going, this way or that way, exactly the same, pull from the zeros. Yes? So very easily, if I give you a pole zero plot, you can eyeball it and see and tell me what the system look like. Yes? This is for 0, right? Pole will be the opposite. pole will be making you stronger, right? And so on. That's why pole cannot be on a unit circle. Why is that? If there's a pole on a unit circle, that's infinity. That's why when you have a stable system, the pole cannot be on a unit circle, right? You know this fact before. Is that clear? Right? So now you can, actually from here you can see it also. That magnitude, that one magnitude 1, that plot right here is cosine omega over 2. You plug in pi, you get cosine pi over 2, that's 0. Yes? Right? So, any questions? Good? So let's take this idea here and just make it a little bit more complicated. So I'm going to give you a whole bunch of zeros, and you can tell me how the system looks like. Right? Okay, so let's take a few more examples. Okay, you tell me where to put the zeros. This is not exactly a circle, so let's see how to do a better job. Let's see. Okay. Well, would you like the zero to be? 1/2 what? What's the phase? Huh? Pi over 2. 1/2 radius, pi over 2 angles. Okay. That's it? Come on. Make it more fun. Yes?
Oh, I don't know, like 0.7 3 over 2.
Oh boy. Now you make it more difficult. Okay? Okay, that's it? All right, that's it. Okay, let's do it together. I have no idea. This is anything wrong, blame your friend, right? Blame them. All right, so you notice that something happened at pi over 2 and 3 pi over 2. So that's 3 pi over 2, right? 3 pi over 2 is minus pi over 2. I'm going this way, right? Some happened at pi over 2. Okay? Now this is going to be hard because they're not really balanced. If this is going to be at 1/2, then think of it symmetric. But it's 0.7. Okay, so I know it's going to be because when I'm starting over here, getting close to pi over 2, there's a dip. I'm getting close to the 0. And the dip will be deeper here. This is closer to me, right? So I know that could be a dip closer there, and a little bit higher here. That's all I know, right? Because relatively speaking, when I'm standing right here on a unit circle, this 0 is closer to me, and I'm over here, right? Besides that, I have no idea. It's going to be, something like this. I don't know. So that's all I know. It's going to be like this. They got to be connected, right? So it'll be the same point. Okay, roughly speaking. Okay, the pole will be the flipped, right? Okay. So let's talk about symmetric response. And linear phase system. Right, here, one example. The impulse response, x of n, is symmetric. How do we know symmetric? Because there's a center of symmetry where this is refractive, right? Okay? So give me another example where the impulse response is symmetric. Let's have a 5 sample. Okay? So let's see. Okay, let's do 0, 1, 2, 3, 4, 5, that's 1. So I choose it very carefully. The center of symmetry at 2. Let's call this is L. L stands for center of symmetry at 2. Okay? Let's say this value here is 1, 1/2, 1/4. Those are the sample value, 1/4, 1/2, 1, 1/2, 1/4. Okay? And I wanted to now to write the Fourier transform. Okay. Now you can plug it in. You can say this is equal to 1/4 plus 1/2 e to the minus j omega, e to the minus j 2 omega, and so on and so forth. It'll be 5 terms. Or you can use a trick that we have over here, finding the center of symmetry, pull out the phase. What's left will be pairs of exponential that make it a cosine. Well, either way works. So now I'm going to do the way that I pull out the center of symmetry. It will be e to the minus j L omega. Right? So 2 omega. What is left will be how many terms left. How many terms will be in this bracket? After I pull out 3 terms, right? There'll be 1 term by itself, and then there's a pair right here, make cosine, and the cosine pairs. And this term here is a constant. It is 1. Right? Because if you do the brute force way, that impulse right here will be 1 e to the minus j 2 omega. Right? Now, what is this pair going to give you? 2 times 1/2 cosine of omega. That distance here is 1 as omega, right? That could be cosine of omega. Again, that's a cosine pair. That's 2 times 1/2, make it 1, times cosine of omega. That's right here. How about the next one? That pair right here gives you 2 times 1/4, that's 1/2. Pair gives you cosine of something omega. What is something here? That's the distance from your sample to the center of symmetry. What's that distance? 2. Okay? So you see that symmetric, you're able to write it in general, right? It would be e to the minus j L omega, or L center of symmetry. L here is 1, L here is 2, L there's 1/2. right? Be a summation. Okay? This here's A of n cosine of n omega. Right? A of 0 is 1. In this case, A of 1 is 1. A of 2 is 1/2 for this case. In general, given any impulse response that is symmetric like this, I can write it in terms of a phase terms times an amplitude terms. And this is always real values, right? The cosine is also always real. Is that clear? The range from 0, that's a constant term, n equal to 0, that's a constant, to what? In general, what do I put here? Here I put 2. In general, I put L. Okay, let me pause for questions. Questions? So this is in the book, right? All the books, this is type 1. Type 1 is symmetric, center of symmetry is on the integer. Let's do a quick one on type 2. And then we'll continue next time, okay? Type 2, let's say you have 1/2, 1, 1, 1/2. At 0, 1, 2, 3. That's the one over there. For this type, center symmetry is on half integer. Right? So for this type, it will be h of e to the j omega. The phase term is exactly the same, right? E to the minus j L omega. L here is 3/2. In the cosine term, I have 2 pairs now. There's no constant anymore, right? 2 pairs. That pair gives me 2 times 1 cosine of omega over 2, 1/2 omega. Right? That could be 2 cosine of omega over 2 plus 2 times 1/2 cosine of 3/2 omega. That's 2 times 1/2 is 1 cosine of 3 omega over 2. Right? So in general, this is e to the minus j L omega summation b of n cosine of n plus 1/2 omega n from 0 to L minus 1, L minus 1/2. Okay, you can actually plug it in and say n equal to 0. This is cosine of omega over 2, and then that 3/2, make it 1, make it 3/2. Okay, so to summarize, symmetric impulse response give you linear phase system. Why is it linear phase? Because you can write the Fourier transform in the phase terms and a real value terms. These have no phase in here. It's real value. So all the phase is in there. And why is it linear? Because this is L omega. That's a phase response. Just a straight line. It's linear. Right? For type 1, center symmetry is on integer. And therefore, there's a constant terms. And all these are integer. For type 2, center of symmetry on a half integer. Therefore, this is half integers. Right? All this is half. All right? On Wednesday, when you come back, we'll have the other type. Well, this is anti-symmetric. Right? So it'll be type 3 and type 4, but very similar to this. Instead of cosine, you have sine. That's it. Okay? I'll see you on Wednesday. And the lecture will be online to that systems about 2 hours after, right now, about 10 o'clock. Pardon me? No, it's on that system, on EVT. So it'll be on evt.ai. Yeah.
Where do we go pick up the books? You said
The book?
yeah.
The book, I will bring the book in on Wednesday. I will give to you. So but make sure you have your partner, the team, okay? Very good.